Hello, Harsha. Harsha, can you hear me?
Yeah, I can hear you.
Yeah.
So do I need to do the homeworks for the other course, the
No, not the homeworks. Just take the test.
test quizzes? Okay,
That's the understanding we have, right?
right.
If you look
Yeah,
at the
I
document.
was just making sure. Is it next week, the test?
No, actually, it was due tomorrow. It's due today, actually, but
Oh,
so it was postponed to Thursday. So yeah, look it up.
oh, okay. I thought it had the same schedule as this one.
No.
Okay.
Can you set something?
Oh, just good morning.
Come on. Come on, let's- Okay. So we had a homework due today. Did that go smoothly?
I'm unfortunately gonna have to turn it in later today.
Okay.
I had some questions regarding last class as well. We can just go, I can ask you that at the end, if that's okay.
Okay. Sure. Yeah, it's up to you. Yeah, I think the due date is 9:30, but I think this homework, it is possible to submit until the end of the day, I think.
Okay.
So, without any postponement necessary. Yeah. So, how's it going, Harsha, for you?
Homework due in the sense, is it 4? Homework 4?
Um, yes, homework
Yeah.
4.
I sent you an email just about a few minutes ago.
Okay, so you submitted. Submit it
Yes.
on D2L, okay? Harsha, it is much more convenient.
Oh, okay. Yeah, I can do that.
Yeah, please do that. I mean, because it's very inconvenient when I have to follow some is in the email, some is here, there. So
Okay,
So
yeah, I did not know about it. I can do that.
Location.
Yeah, I know how to do it.
Yeah. So just do it on detour. This homework 5. That's due March 2nd. That's next Tuesday. It's very similar problems. The spirit is the same. We're minimizing some quantity. The context is different. Earlier we did optics. Now we will do minimization. The 3 basic, or at least 3, you can think of that. The examples that I do work with. So that's Fermat's theorem. Right, that's one. The second is when the distances are minimized, those are called geodesics. And the third is when the time is, not only time in a gravitational field is minimized, that's called a brachistropron. Brachistropron itself is a very special case when you're talking about uniform gravity, but you can extend this for a class of brachystroprons if you want. There's, of course, you can keep going. There are minimal surfaces, like what is the geometry of a water bubble, for example? What is the geometry of a drop of liquid? So those kind of problems are all there, but these are the 3 basic ones I have been using. So that's this homework will work with. I think it's a one. No, it's a brachistropron problem, I think. And there's a midterm of 1. So notice this is different from, I don't think either of you are there in the other class, right? So this is going to be in class next week, Tuesday. So this is March 2nd, Tuesday. Is that okay with, since both of you are here? So Ken, you have been coming. Harsha, is it okay? You do come to the department, right, for teaching and all that?
Yeah, that's okay with me.
Yeah. So. And it will be just a timed example. Okay. Question? Yes. Ken.
We have like the class period amount of time. I think it's like an hour and 15 to do the.
Yes. Are you guys free after this class?
I mean, yes.
How long are you free? Half an hour?
On Tuesdays, I'll be free till 12. Yeah.
So, Harsha, are you free after this class period? Harsha?
Yeah, I'm free after this class.
Yes. So take reasonable amount of time after the exam will be for 1 hour and 15 minutes, but feel free to take extra time. Reasonable amount, it shouldn't be that for 5 hours I'm waiting and doing it. So most probably in 2 hours you cannot finish it, but probably it may not work out. Yeah. So so time need not be a constraint. And I don't intend to test it significantly hard or anything, very closely related problems. It's just that you may not have the notes and resources available. That will be the only difference. Okay. So yeah, that's all. Anything else I should be specifying? And notice the homework is due right before the class, but I think we did enough examples, so now by now it's clear. So it will be all functional derivative and the minimization problems. Okay. Okay. Let's do another minimization problem. So Fermat's theorem was minimizing time basically. Now let's, and we did do a geodesic on a plane. That was a very simple one. Now we can talk about geodesic on a surface of a sphere. on the surface of a sphere. A simple, trivial problem could be you're flying from one point on Earth, one city to another city, and you want to save the amount of fuel that is used up by the airplane. So you want to take the shortest path, and what's the path? So given 2 points on a sphere, what is the shortest path? So first of all, what is the coordinates used in on a sphere? So that's your sphere. Let's say typically we use latitude and longitude, right? So let's say, so let's first of all have this to be your angle theta, and if I were to, let's see, so that's a point on the sphere. Okay, that's reasonable. And x and y, right? So this is, let's say, x, that's your y, that's your z, and this is angle phi. Notice that in mathematics, they flip this coordinate. Theta is the polar angle and phi is the azimuth angle. So in math books, it is always flipped. So be aware of that. Longitude phi is the longitude. If you were to specify a city, you would say on which longitude it is. I think it's also called a meridian, I suppose. Is that correct? Meridian, yeah. So we are about how many? Like about how much? So 24 hours is about 360 degrees. So each hour is how much? How many degrees are we to the negative side of London? So 360 divided by 24. So that will be 4 plus 4, 12, 12, about 15 maybe. So 15 into 7, or 15 into 6 approximately, correct? So that's about, so we are probably about 90 degrees, minus 90 degrees. So phi goes from, we will have phi going from 0 to 2 pi. But when you talk in terms of longitude, this is actually, so longitude will be, what is it in terms of phi? So that's phi minus pi. So longitude is so phi minus, longitude is equal to phi minus pi. The typical spherical coordinate minus the pi gives you. So long. For Carbondale, it's about minus 90 degrees. Oh, he left, I guess. Okay, what do you think you can? Ah, Harsha. Hello, Harsha.
Yeah, I think you got disconnected. I also reconnected.
Yes, yes, yes. I think Ken pointed it out to me probably after a few minutes. Yeah, I think the computer sometimes starts what is it called? Updating itself on its own. So
Hmm.
it decided to update it at this point. so, so yeah, but hopefully we didn't cover much. So it is just I was introducing the angles and theta and phi. But,
Yeah.
okay. So again, longitude is phi minus pi, latitude is pi by 2 minus theta, and theta and phi are spherical coordinates. For Carbondale, it is just nice to be aware that it is. So for Carbondale, this is approximately minus 90 degrees, I think so. I just calculated it now very roughly. And latitude is, this I know is about 38 degrees. And it can be up or down, so it is not, let's say, positive or negative in this case. But when you're doing it theta, you don't have to specify anything. Theta is between 0 and pi. Okay, so the idea is that if you give 2 points, theta 1, phi 1, to theta 2, phi 2, these could be 2 cities. What's the shortest path connecting them? And we are going by shortest path as a function of distance. So of course, let's say L, right? So it's good to define L. So L, right? L is the length of the path, and it could be we are defined as a function, but as of now, this is an integral starting from theta 1, comma phi 1, and going to theta 2, comma phi 2, and you have to add up all tiny elements. If you have a surface, that's your ds. So as far as you know how to measure this tiny element, you can just have to keep adding it up. This is on the surface of a sphere, so we have to use we can use spherical polar coordinates, and the distance on a sphere is given by if the radius is known, so it is r times d theta. It's small, it's fixed actually. It's r times d theta square plus r times sine theta d phi square. Is that familiar concept, or should I be motivating that any more?
Yeah, it's good.
Yeah, should be clear, right, Harsha?
Yeah.
Yeah. Okay. So that's your ds. If I want to replace this, notice that it can be done in 2 different ways. I can write this as ds is equal to, I can pull out a r d theta and write this as 1 plus sine square theta d phi by d theta square, or I can write this as ds is equal to, I can pull out the d phi. Let me pull out the whole sine theta also. So this is half sine theta d phi, and 1 plus, so then the sine theta goes in the denominator, right? So it is, we have 1 over sine square theta d theta over d phi square. Just by In general, it is okay to pick anyone, but often what happens is that one of the ways is usually much simpler than the other one. And in this case, we notice that this is, first of all, it's in the numerator that itself actually saves a lot of trouble. So we will see phi as a function of theta. So we would like to think of L as a functional of phi. So phi as a function of angle theta, and we are asking for which function, which particular function theta does this actually minimize the power. So that's equal to, so I don't have to write write theta 1, we go along theta, right? So this is theta 1 to theta 2, and phi is a function of theta. So ds is r d theta, r can come out, so it's r d theta, and 1 plus sine square theta d phi over d theta. Is that correct? Okay. We want to minimize this, so immediately we do the functional derivative. So let's do the functional derivative and we'll come back and say that that's equal to 0. So we would like to find what is dl change in the functional with respect to a change in the function phi as a function of theta. Since I'm going to take a derivative with theta, it is good to make all this theta prime. Theta prime, all the dependence is theta prime. Okay. So that's the same as limit delta phi tends to 0 to L of phi plus delta phi minus of phi divided by delta phi. So let's see what that change is. Let's go to the other board. I think we did reasonable. This example also I'll do it a little slowly, but the idea is that very soon we'll get efficient at this. Okay, so L phi plus delta phi is equal to theta 1, theta 2, theta or d theta actually, and anything else, that's theta prime 1 plus, wherever I see a phi, I have to change it to phi plus delta phi. So that's sine square theta prime d phi by d theta prime. So that's a function of theta prime plus delta phi of theta prime. And I have to make the square root. So there was just this d phi by d theta whole square. I replace the phi with phi plus delta phi. So that's the change in the functional. I have to keep only the leading order term because when I subtract it out, or not the leading next to leading order term, because when I subtract to find the change, the leading order will cancel out, and the next to leading order is what contributes. So that's equal to theta 1 to theta 2 or theta prime. Let's do this in 2 steps maybe. So this is 1 plus sine square theta prime d phi by d theta prime. That's your original term itself. And there are 2 terms, like basically 3 terms when you expand this out, at least the square part. the last one is a second order in delta phi. I'll just drop it right away. And this is sine square theta prime 2 times d phi d theta prime and d by d theta prime delta phi of theta prime. And this whole thing is square root. Expand this out again. Square root itself is raised to half. So binomial expand it and keep it only the first term. So I have that's 1 plus. So that's my original functional itself. And when whatever is remaining will be 1 plus this whole quantity divided by this, and I'm going to expand the square root. So we have 1 over 2, and whole thing remains. So the sine square theta prime 2 times d phi by d theta prime. Hopefully that's visible to in Harsha. It's 1 plus. And that's all that's needed. The next term is higher. Is that clear? Any questions? One should get fluent with these things soon. The 2 cancels out, and when we subtract out the original function of this one first term, all of it cancels out. So delta L would be so delta L as a function of phi would be equal to that still, yeah, maybe Christian pen. So that's just this term multiplied by this. This is theta 1, theta 2 of theta prime. Square root cancels partly the denominator, so we have sine square theta prime d phi d prime. And there's one more term, which is d by d theta. This is very similar to what, if you've seen it in undergrad, what is called Euler-Lagrange function, but this is from a very scratch. We are doing Euler-Lagrange is only when the derivatives of when they're functions of linear derivatives alone. So it's a small specialization. But for most of the examples, it goes through identical. Okay, so that's all variation. The change would be divide this out. So I need the functional derivative would be divide out by delta phi theta, but the variation here is actually a function of theta. Since it's a function of theta and this is theta prime, it can actually go through the whole integral. It can even go through this derivative. Everything is theta prime, and we will place it right here. So it's theta 1, theta 2, theta prime, sine square theta prime. just to clarify, this is also a function of theta prime there. So that's 1 plus. This is also a function of theta prime. And this is d by d theta prime. And we have theta prime over theta. And we said this is a limit, right? In the limit, delta phi tends to 0. We said this is a delta function, and that's because the variation in theta with respect to theta prime. So phi is a function of theta, and two different points at point theta are completely independent. The variations we make there are absolutely independent of each other, very much like in rectangle. If you're in 3 space dimensions, when you take gradient, that's like partial derivatives, so they are completely independent. In that spirit, this has to be a delta function, we said. So this is delta function of theta minus theta prime. Right. So always that shows up because leading order is what contributes. That is the only term actually always true. Once we have this is a delta function, derivative of a delta function. So how do we evaluate an integral that has a derivative of a delta function? You integrate by parts. You put this all on the other side. When you integrate by parts, this has two surface terms, but we are saying that there is no variation at the boundary. So with that two information that we have used earlier, with that fact, we can write this immediately. And we'll come back later on and do this more carefully when the boundary terms actually has some meaning in there. So this is R. So integral is getting done. So this is theta prime, actually minus sign because there's an integration by parts in there. And this whole thing sine square theta prime d phi over dt. Actually now it is theta, right? Because we've done the integral. This is d phi by d theta over 1 plus sine square theta d phi by d theta square. That's your functional derivative if you want, or the change in the functional with respect to a arbitrary variation in the function. But we want this to be minimized. So we said we are looking for that particular path for which this variation is 0 in the leading order if it is, or the next to leading order if it is 0. That means this is a minimum, right? That is like the slope being 0 or the velocity being 0 in a position time graph. So if we set this equal to 0, that's our equation for phi. So that leads to a differential equation. So the minimization condition implies, if I can write that here. So this is the derivative of this is equal to 0. So that means that sine square theta d phi by d theta divided by 1 plus sine square theta sine square theta d phi by theta square root of this has to be equal to a constant. So let me call that C. So that's our differential equation. So if I rearrange this and write all the d phi by d theta together, this gives me a differential equation for phi. And from that point on, it is a matter of solving the differential equation and getting phi as a function of theta. Any questions at this stage? Two steps we have done here. One is the actual minimization principle itself. And the second, which I have been trying to go slow is the functional derivative. The rest everything should be the techniques that you have seen before, and you're seeing it in a different context. That's all. Okay, so let's rewrite that differential equation and try to solve it. So let's square that equation. So we have sine raised to 4 theta d phi by d theta squared is equal to c squared. C squared plus c squared times sine squared theta d phi by d theta squared. Right, that's what it is. Collect them together. So put this and this together, right? So we learned that d phi by d theta is equal to c squared, or take a square root afterwards. Right? C help. So put it on the other side. So this is c divided by, which is a sine 4 here, sine square, so I can take out sine square. But then I'm taking square root, so it's sine theta, and then I think that's correct. Check on me. So yeah, that's correct. That's the first order differential equation, and we are good if we can actually integrate it. And of course, c is an arbitrary constant at this point because this was obtained from the first integration. You can say it's an integration. You said derivative of something is a constant, so we are basically that means that that's a constant of integration. And we will try to find that out also, but at the end, since it's going to be a sphere, we will just see, at least it will be clear enough what that C stands for. Okay, so that's your differential equation. So let's put the C d theta also that side. And that's the same as C d theta. And if I were to integrate this, integrate on both sides, we have phi minus phi naught. This is an integration constant at this point, even though it looks like some initial time. So that's a constant for all the both the integrals here, and right side is. So how do you do this integral? Let's see. Let's rewrite in terms of replace this as a cotangent maybe. So cotangent and sine theta is cosecant, right? So this is C cosecant theta d theta. And pull this out also, sine square theta gives you another cosecant square theta divided by 1 minus c square. This becomes c square over sine square theta, which is again a cosecant square theta. Probably. Remember, we have one plus cotangent square theta, right? That's equal to, there is a cosine square over sine square theta. So that's cosecant square theta. So that's an identity. So it seems like it might be good if I can identify such an expression in the denominator, right? Because then I can substitute cotangent theta is equal to some function. So replace this with that. So I think that might be a good idea. So let's equal to. So this is an integral when you went from phi to. This is okay, and this is integral by the way. So indefinite. Okay, so what do I do? Yeah, I think just let's substitute. I think this works. Cotangent theta is equal to, let's say, t. And derivative of this is what? Dt is equal to, what's the derivative of cotangent? Cosine theta. So that's minus sine theta, so it's minus 1. And then that's minus of minus cosecant square, right? Cosine theta over minus 1 over cotangent square. That's a derivative of that, but then 1 plus cotangent is cosecant, so that's minus cosecant square. So dt is cosecant square theta d theta. Okay, so that's better. So let's try this out. And I'm still hopefully in the board space. So that's equal to integral of c times dt and 1 minus c squared times cosecant square theta is 1 plus t squared. So it's 1 plus t squared, so that's minus c squared t squared. Is that clear? Yeah.
Is that minus cosecant squared?
Yes, so what I did was this one here. So what I did was d by d theta. So maybe I should do this more explicitly. I was just doing it for myself. So d by d theta of cotangent theta is equal to d by d theta of sine theta or sine theta. That's how I do it. I mean, there might be better ways of easier ways of doing it. So when you take the numerator, so that's minus sine theta over sine theta, so that's minus 1. And when you do the denominator, you do cosine theta divided by sine square theta, and then you take the derivative of sine theta itself. So that's cosine square theta over sine square theta. That's equal to minus 1 minus cotangent square theta, but that's the same as minus cosecant square theta. But that's typically if you're using this often, then you just know it as an identity. Okay. Okay, so that's quantity there. So let me, I should be able to do something, right? So let me, yeah, this is a constant here, so let's pull it out. That's trivial steps actually, but still 1 minus 1 over c squared dt over 1 minus c squared over 1 minus c squared times d squared. Let's define c bar to be c over 1 minus c squared. Same constant. This is a constant, so it will also be a constant. In that case, this is c bar squared. This is c bar. So this whole thing comes down to. There must be a single substitution that does it. I'm just doing this in multiple steps. C bar p whole square. Okay. So pull it down. Okay. At this stage, it is clear this must be some sign, right? So again, substitute c bar t is equal to sine of what should we call it? Let's call it sine theta prime. Theta prime. So probably right there. There must have been some symbol. Seems like I'm going in seconds. So c bar dt is equal to cosine theta prime d theta prime. Right, that makes this doable. So this is cosine theta prime, d theta prime. And in the denominator, this is 1 minus sine square. That's nice because these two cancel out. 1 minus sine square theta cancels that. And this is just theta prime. So what we have is phi minus phi naught, that was an integral constant, is equal to theta prime. Right? But theta prime was, we made a few substitutions. We have to go back now, right? We have to get back our original theta, right? So theta prime was sine inverse of c bar t. So that's equal to sine inverse of c bar t. And t was cotangent theta. So that's equal to sine inverse of c bar cotangent theta. That's how you would do this. Okay, all this we have, don't forget the original problem, but we're trying to minimize something, 2 points on a sphere, what is the shortest path, right? So what we're saying is that a function phi is a function of theta. This is the equation that minimizes it. And so let's try to interpret this. The sine of phi minus phi naught is equal to c bar cotangent theta. How do we see this as an equation of a minimal curve on a surface? So let's try to rewrite this in a certain form. So our equation is sine phi minus phi naught is equal to c bar times cotangent theta, so that's cosine theta over sine theta. So right, multiply the sine theta on the left hand side, or before that actually expand this. So this is sine of phi cosine of phi naught minus of cosine of phi times sine of phi naught. Expand this out, that's equal to c bar cosine theta, and let's also see this as sine theta. Rewrite it this way. And we see some spherical coordinates, right? And this is sine phi times cosine phi. And this is minus of sine theta cosine. Oh, maybe I should write it. So first let me write the second term. So it's minus sine theta cosine phi times sine of phi naught. And then there's plus sine theta sine phi times cosine of phi naught. So that's the first term. And then there's minus cosine theta times c bar. Right? If you notice the sine theta cosine phi, like suppose there is a vector r, and on the surface of a sphere, a vector r, let's say r, or a coordinate position, that's that will be r sine theta sine phi, cosine phi. Then there is r sine theta sine phi, and there's cosine theta. That will be your vector r. Let's think of another vector. Let's say n, vector n. That's equal to minus sine phi naught here. I'm just reading off whatever is left out. And this is plus cosine phi naught, and there is minus c bar. In that form, notice again that this is your x. X, that's your y, and that's your z. And this could be nx, ny, and z, what we have is R dotted with N is equal to 0. So whatever this equation is, it is selecting. So this is a vector, a fixed vector in space, and this is actually picking out all the points on the sphere which is perpendicular to the vector n, or you can write x times nx plus that's a component of the vector n times ny plus z times nz is equal to 0. That's another way of writing this. So again, think of a sphere. So again, think of a sphere. There is some vector n in some direction, so that's your n. And all the points on the sphere, all those points x, y, z, or all the coordinates on the surface of a sphere which are perpendicular to this. Like this point is not perpendicular, so there is this point that is perpendicular. But then you would say, oh, this is also perpendicular, right? How do we know that this is actually which of those circles, right? There is a whole set of circles that are perpendicular to that and hat. But now notice there is one point which is very clear that x, y, z, this is an equation of a plane, and x equal to 0, y equal to 0, z equal to 0 is part of the plane. So the origin, so this plane, if you think of this as a plane, so the plane that picks that circle passes through the origin. Right? This is also an equation of a plane. So this is not just that particular, any circle that is perpendicular to n hat. So you have to pick the one that passes through the origin. So that's called a great circle. So, so this is a great circle. So out of all circles, the one that passes through the center of the sphere is what connects, gives you the shortest path. So what the answer to be having a shortest path, you have, let's say these are the 2 points. You're going from New York to London, let's say. So that's your 2 points. Find the circle of all possible circles that can pass through those 2 lines. Find the circle which, when extended out, is actually having its center right at the center of the sphere. So that will be the 2 curve that will connect it. So that's θ1 phi 1, that's θ2 phi 2, and that's your shortest path. Is that clear? Of course, you can go the other way also. Among the 2, you pick the shorter one. Is that clear how I concluded that? Any questions on that? Yes.
So you said x, when you make x, y, z equal to 0, you're mimicking the plane at the origin?
No, what I meant was that, okay, so this is, first of all the points on the sphere which are perpendicular to the vector n satisfy this condition. So one would think that, oh, this is also such a circle, right? All the points on that. But then you realize that, oh, this is also an equation of a plane. Like this, if I explicitly write it in this form, so that's also an equation of a plane. And in that plane, there is a point x, y, z, which is satisfying this equation. That means that whatever this curve is, that has to pass through the origin. So the circle is not just any circle, it is the circle that has a center coinciding with the sphere. So the point is, in general, this could, as an equation of a plane, could also be non-zero. Right? This is an equation of a plane that actually is equal to 0. So that actually selects the great circle. So the simple answer is, of course, that it's a great circle. Right? But we went through the whole details and got this. Yes, Christian?
This will be different than if we were to like minimize the time it would take to travel.
Yes, if it is minimizing time, because time will depend on the velocity, right? So what we did was, good question actually. So what we did here is that right, that's a simple velocity here. But now time would be ds over velocity. So now the question is, what is the profile of the velocity on the surface of the sphere? Right? You can say that, think of a climate where that air is denser in one region, air is not denser. Like for example, based on the weather, you could have wind in one direction and in certain regions of your travel, and wind in opposite direction in another region of travel. So that gives you a velocity profile, which could be dependent on theta and phi. So give me the velocity profile and I can calculate the time. So this will involve a little more work, or I wouldn't say little more work, it will involve a different integral. And based on the profile, it might be solvable or not. I shouldn't say not solvable, it's always solvable, it's just that it may not come out in elementary functions. In this case, we got a very simple solution.
So that would be like a functional with two variables.
It will still be a function of a single variable, right? So remember, this was also theta and phi, right? Theta 1, phi 1 to theta 2, phi 2. You want to go from one point to the other point, but then you choose one of them as a function of the other.
I see.
Right? So you always pick one to be the function of the other. You do the same thing here also. So it is a single variable problem. So this will be doable. It's just that the profile is not, I don't know the profile.
Yeah.
It's a very specific problem. In this case, it's a classic problem. Here, it depends on the profile. It's exactly like the Fermat's theorem. Fermat's theorem depends on what medium I choose, right? I did an example in the class, and then in the homework, you did another example. So in general, it's different. So given a profile of velocity, you can actually work on it. Right? You can always ask the question that just to create an example of what you could do. So think of this is north and south hemisphere, and maybe you're traveling on one of the days. The winds are sorry, the Earth is going this way. This winds are this way, right? So when you're you can put some functional dependence on that. And then you say that when I'm going that side, I have one profile, and while coming back, I have another profile. So which way do you do if I had to make the round trip? How do you get that? So you can construct interesting problems.
Very similar to Fermat's principle.
Yeah, but after that, it is exactly Fermat's. Yeah, exactly. It's just that this is in spherical coordinates. That was in XY coordinates. This is in spherical coordinates. Yeah, very good. Yeah. Yeah.
Thank you.
Yeah. And it might be, since there we saw an example where it can go in a circle. Here also you can think of what kind of profile will actually, if you go around in the circle, it might be more beneficial than going straight. So one can ask such questions. Yes. Yeah. Okay. Any other comments, questions? Okay. So let's define what the classic brachistochrone problem is. Erase this. Okay. I'll just define it and probably. Chrome. And I should point out that whenever we do these kind of problems, you can generalize it very easily. For example, I can do this for any surface, right? You did this for a sphere, you can do this on a cylinder, you can do this on a cone, you can do, as you said, the velocity profile. One of the interesting things is when you do this on a race car, right? If you're going in a circle, there is a limit on how fast you can go. If you remember your undergraduate physics, if you go faster than a certain velocity, you will slip. Like if you're on a speedway, let's say. If you're going slower than some velocity, you will slip again in the inward direction. So you have a window of velocity profile you can have. And usually if you're driving a car, you want to go from one point to the other in the shortest time. And that's exactly your problem. So it will be a minimization problem on the surface of a cone now, with the velocity profile decided by the slip conditions. And that can be analyzed, and it has solutions that comes out very nice. So it's kind of neat little problems you can build on that. But it's interesting to note that all of this minimization problems in the functional sense, notice these are infinite variable minimization problems, not a single variable. This all started with the problem, the first problem ever solved, at least, which is written down, is the Brachistochrone problem. And historically, how it worked out is that apparently Bernoulli came up with this problem, probably in 1608. It must be after Newton invented his calculus, because so 1660s is when he gave his Newton's laws. And so this must be about 1670s or 1680s. So he came up with this problem probably around 1670s. I do not check that, but it is very well documented. But he thought this was an interesting problem, so he gave it as a like in those days, you just have newsletters and you advertise it. He challenged that who can solve this. And apparently he got some 3 or 4 solutions. He obviously solved it before, but Newton was one of the ones who solved this problem. But Bernoulli most probably solved it beforehand when he gave the question itself. So it's credited to Bernoulli. So the question you ask is, you have a point, right? So let's say this is gravity, uniform gravity. So this is on the surface of Earth. G is a constant, and if you were to drop something here from a certain height, let's say this is x1, y1. Everything is happening in a plane, so we can always pick a slice in the in Z, and let's say you want to reach x2, y2. So that's another point in this plane of the board. And let's say you just drop a rolling ball. Let's make it simple. Let's just say this is just sliding. So this could be there is a small ring-like structure, and this is a rod, and it is just sliding on it. I can make it roll also. The same thing works except for some constants. So all this goes through immediately. So, and it goes from the top to the bottom. And what Bernoulli asked is, okay, what will happen if I were to actually go all the way straight down and then make a small slope there? So if you go straight down here, you gain a lot of velocity, right? So in that sense, once you have gained a velocity, then you can go this part of the distance very fast. So but then you're traveling a longer distance. So this is a larger on distance, large distance, but high velocity. This is smaller distance, lower velocity. And immediately you come, whenever there is this dilemma that one is better than the other, two parameters which are pulling the other way. So it seems like there must be a path in between which will be balancing the other, right? You can even actually go all the way. One can argue that you can actually go all the way here and come back. So you're gaining a lot of velocity. So you will be going very quick here. And then you reach there. So is this going, will you have any advantage of doing that? So the question comes, what is the best path you have to take from going from x1, y1 to x2, y2 so that you reach in the shortest time? And that path is called Brachiostrict run. And how would you do this time, right? So you immediately do the our same principle. Right? So you have t, the time taken would be equal to go from x1, y1 to x2, y2. And time is distance, ds, divided by the velocity, right? And velocity along the path. So what is the velocity? So what is the velocity profile on the path? That's decided by conservation of energy, right? In this case, it is governed by conservation principle. So let's remember that whenever something is falling under gravity, you have, and since gravity is a conserved force, we have half mv squared plus mg h, right? So I had to now decide, so whenever we do this gravitational potential energy, I have to have a reference point. So let's say everything is referred with respect to somewhere here y equal to 0. Wherever my origin of y is, I don't specify where it is. If it is here, so that's my distance y1, that's my distance y2, but it could be anywhere up or down. So there is a reference point y equal to 0, and this is mg1. And that has to be equal, so this is conserved. So that has to be equal to the velocity of mv1 square plus mgy1. For that matter, it should also be equal to mv2, right? Doesn't matter. So it's just saying that it's all conserved. So at any point on the path, there is a height y and velocity v, right? That's governed by this equation. Let's consider a specific example where it is starting from rest. So let's let v1 be equal to 0. So initial velocity is equal to 0. In that case, I have half mv square plus mg y is equal to mgy1. So v1 cancels out. I can get rid of the mass m, and I can solve for v now. And I have the profile then, right? So v is equal to 2 times g y1 minus y. And that gives me the profile. And then it is, this is x1, y1, x2, y2, and ds over 2 times g y1 minus 1 square root. again, we'll split ds into dx and dy and try to minimize this, but let's do this in the next class. I won't be able to finish this, but that should give you a full feel for what it is. Any questions at this stage?
Our limits don't change because of our DS, right?
Yes, because we are in DS. The moment I go to, let's say, y is a function of x, then I would say this is equal to, so let's say this is x1 to x2 dx, then this is 1 plus dy by dx square root of that divided by, so this is 2g, it's a constant, and this is y1. Was that your question? Yes.
Thank you.
Yeah.
I'll just wait.
Yeah, good. Okay, yeah, let me not proceed here because it won't get over, and then anyway, I'll have a.
So with a lot of the minimizing the time it takes
Mhm.
on a specific path, finding the velocity profile will pretty much set you up for the general,
Mhm.
like the general path to the solution. Right?
That's good. That's good. And why we're doing all this is that now we're going to say that Newton's law itself is a solution to a minimization problem. And that will introduce us to Lagrangian and Hamiltonian. Okay. Thank you. Yes. Harsha, comments?
Hmm. I don't have anything to say.
Tell it again.
Oh, I don't have any questions.
Sure. Yeah, yeah. Okay, that's all. Yeah, you must have seen this before, I suppose, right?
Yes, I did.
Good. Okay. Okay, I'll stop then. Okay, stop. Bye. Have a good day.
Yeah, bye.
Mhm.